Well, hello again. Intro to College Physics, guys. We're going to be doing notes on Chapter 5, Section 3 about gravitational potential energy. Before I give you the definition for that, I want to remind you that our definition of energy is anything that has the ability to do work. So if you consider an object that's elevated and you drop it, it can go and hit another object and cause it to move. Therefore, it has the potential to do work. So we have gravitational potential energy. The definition is energy an object possesses because of its position. If an object is allowed to fall, the work done will be equal to, and it's the same equation we've been working with, force times delta y. We changed it to a y because we're talking about vertical displacement this time instead of horizontal. Well, the force is its weight, mg, and delta y is the height. And so the potential energy an object has is equal to mgh. This is scribbled out here. So it's just mgh. And we know that work net also equals the change in kinetic energy. And so if we look at the object before you drop it, it has zero kinetic energy, so the initial is zero. And then what we'll have is work net equals 1/2 mv squared. Well, we just showed that work net is mgy for an object falling up here, so we can set up mgy equal to 1/2 mv squared. The m's cancel out. Solving for v, we get v equals the square root of 2g times the height, 2g delta y. You will use that equation quite often. For some reason, I had that picture in there twice. Okay, so we have conservation mechanical energy. Mechanical energy is the sum of an object's potential energy plus its kinetic energy. And if we don't have any non-conservative forces, or if we don't have any non-conservative things, like if you push a book in any route except for a straight line from point A to B, you'll have non-conservative work being done. So ignoring those two examples, the kinetic energy plus the potential energy initial will equal the kinetic plus the potential final. Our book uses the symbol capital E for mechanical energy, so we can say that mechanical energy is the sum of kinetic energy and potential energy. And as we just stated, mechanical energy remains constant if there is no non-conservative work being done. So if non-conservative work is equal to zero, then the sum of your kinetic and potential energy will be equal before and after an event occurs. So applying these principles, we're going to look at a few example problems here. The first example problem, we have a high dive platform that's 10 meters, and we have a diver of unknown mass, and we are going to figure out the velocity that the diver has after he's gone 5 meters down and the velocity he hits the water with. And so in solving these, so what velocity does the diver have after he's 5 meters below the high dive platform? We're going to say that the mechanical energy before he starts his dive and the mechanical energy at 5 meters are going to be equal. Now, I'm going to say, since we're finding the velocity at 5 meters, I'm going to call 5 meters our 0 point. And you can call your reference point, your 0 point, any position you want, and you'll still be able to solve the problem. So we're just going to arbitrarily call that 0. And then what we have is we have 0 kinetic energy when he's on the platform because he has no velocity. It's all in gravitational potential energy equals to the kinetic energy final. And because we're calling 5 meters our 0 point, We have no potential energy at that height. So we see here again the masses divide out. We end up with that equation that I just derived for you earlier, where velocity equals the square root of 2gy. And when we multiply that out, we end up getting 9.9 meters per second. Part B is to solve what is the velocity that he hits the water with. And we don't have to redo this equation here. We've already done it twice. Velocity is going to equal 2g times the height. And this time the height is 10 meters because we're going to call the water our 0 meter or our reference height. And so we end up with 14 meters per second. All right, then example 5.6. We have this Daryl wannabe, a little grasshopper, who is jumping at 45 degrees at some initial velocity. At the top of its jump here, it's going to have no y velocity. So its entire velocity at this point is going to be vx. So at the beginning, it has no height. So all of its kinetic energy all of its mechanical energy is kinetic energy, which would be 1/2 mvo squared. Here we have both kinetic energy, 1/2 times vx squared, and we have gravitational potential energy, which would be mgh with a height of 1. So looking at our equation, I have that expressed here. No potential energy at the beginning because 0 height. So then our initial kinetic energy is going to equal our final potential energy plus our final kinetic energy. Scrolling down, there's a bit of delay on my scrolling here. Scrolling down, you see that the masses will cancel out. So then we have 1/2 VO squared equals GH plus 1/2 V squared. And putting some terms in there, our V, remember, is Vx, and Vx is VO cosine theta. So this becomes VO cosine theta squared. Rearranging the equation, I'm going to subtract that term from both sides, and I have this. And then I'm going to pull the VO squared out, so then I have VO squared times 1/2 minus 1/2 cosine theta squared equals GH. And so then I'm going to divide both sides by what's in this parentheses and take the square root to find my initial velocity. Well, this term right here, 1/2 minus 1/2 cosine theta squared, is 0.25. So I end up with the square root of GH divided by 0.25. And when I do that, we find out that that little grasshopper is leaving the ground with an initial velocity of 6.26 meters per second. That's pretty fast. All right, example 5.7. Again, we do not have to come up with this formula because we've done it 3 times now. V equals the square root of 2gh. And so the velocity that the person is going to have when they go down the 72-foot water slide is 20.7 meters per second. And that's assuming no friction. Well, then part B, they go, well, there is friction. And the friction causes it so that the final velocity is 18 meters per second. So we've lost 2.7 meters per second. Now, there's a couple of different ways to find out the non-conservative work, but the way I've chosen to do it is using my idea here of, and this equation is given in the book, if we have non-conservative work in there, then we're going to have the kinetic energy final minus the kinetic energy initial plus the potential energy final minus the potential energy initial. The difference between those two numbers is going to give us our non-conservative work. So we'll find out how much work was lost due to friction. Well, there was no kinetic energy to begin with when she was at the top of the slide, and there is no potential energy at the bottom because she has no height. So it simplifies down to Ke minus PeO. And so we have 1 half mv squared minus mgh. And plugging in our numbers, we end up with a negative 3,160 joules. Well, where does that energy go? Most of it goes into the form of friction, or because it's friction, goes into the form of heat. Now, in example 5.8, we have a skier who's at a hill that's 20 meters high. Now, if there's no friction, we can consider the speed at the bottom of the hill will be exactly what the skier would have if the skier fell straight down the 20 meters. Now, this only works under two conditions. One, you have no friction on the hill, obviously. But two, this is sliding down. It's not rolling. Because if it was rolling, the problem would be a little bit more complex because you're putting a rotational energy into the system as it goes down. So if an object rolls down a hill, it will actually end up being slower at the bottom of the hill than it slides down a frictionless surface. All right, so the second part of the question is, when it gets to the bottom, there is friction, and the friction has a coefficient of kinetic friction of 0.21. So the question is, how far will the skier go? Well, to find A, the velocity at point B, again, all we have to do is use the same equation we have been using. Final velocity equals the square root of 2gh, or 2gy. And we end up with 19.8 meters per second. B, we could go back and use our kinematic equations, but because this chapter is about energy, I'm going to use a method that applies the work energy theorem. And the work energy theorem says that the work net will be equal to the force times the distance. Work net, using our work energy theorem, also would be equal to the change in kinetic energy. Now, we don't have potential energy in here because once it gets to the bottom of the hill, the height's not changing. So we could put potential energy in there, but potential energy is remaining constant the whole time. So there's zero change in potential energy. So it's only the change in kinetic energy for this part. So then we have a formula here where friction times distance equals final kinetic energy, which is zero, so that drops out, minus initial kinetic energy. Solving for distance, which is x, we end up with this equation here. The mass cancels out, so again, it doesn't matter how big the skier is, we'll get the same answer. And so we have v squared, which we calculated in part A, is 19.8 squared, divided by 2, divided by g, divided by the coefficient of kinetic friction. And we end up with 95.2 meters. I hope this was helpful to you. You can use these sample problems to help you in solving your problems in the problem set. And tomorrow I'll put together a video that deals with the next section in our book. Thank you, Hannah. Have a great day.